Good morning. Today we're going over our first homework assignment on covalent compounds, and this covers the structures and shapes of general properties of covalent compounds. And this is going to be a little bit of a long homework assignment. It's a little involved, so I hope this is helpful, and let's get started. So our first problem here, we're looking at what kind of bonds are formed. And the key here is to say if I have a metal with a nonmetal, then that will form an ionic bond. And if you have two nonmetals together, then that's going to form a covalent bond. And being able to quickly and easily identify which of those is going to be formed is really important in order for you to name compounds and in order to predict structures and properties of those compounds. So that's what this first section is about. So I've got my periodic table here. We can see, again, you don't have to memorize these, so might be helpful. We've got magnesium and oxygen. So magnesium is over here, it's a metal. Oxygen's over here, it's a nonmetal, so that will be ionic. Calcium and chlorine. Calcium's here, it's a metal. Chlorine is here, it's a nonmetal, so that will be ionic. Potassium and bromine. Potassium is here, it's a metal. Bromine is here, it's a nonmetal, so that is ionic. Zinc and fluorine. Zinc is here, it's a metal. Fluorine's here, that's a nonmetal, so that is ionic. Chlorine and chlorine, if I have two chlorine atoms, they're both nonmetals, so that would be covalent. Now your options might be slightly different than mine, but that's how you do it. Check for metals and nonmetals. The truth is a little more complicated than that, but for the purposes of this class, we're going to keep it very simple. If you just follow that rule, you'll do great. So next, which is not correct for molecular compounds. And molecular compounds, that's another way of saying covalent compounds. So smallest components are always neutral. That's true because molecules are neutral. If I'm not neutral, then I'm an ion instead. So compounds are made of molecules which are neutral. They don't conduct electricity. That's true of metals, and that's true of water if I have ionic compounds dissolved in it. But it's not so true for molecular compounds. And this is what we just said on our last problem. They have nonmetals with nonmetals, and they do have relatively low melting points and boiling points. So the smallest possible unit of a covalent compound or a molecular compound is the molecule. And what other properties could describe covalent compounds? This is ionic compounds, right? They conduct electricity when dissolved. If I've got a metal and nonmetal, that would be ionic. Gases at room temperature, yes, because they have really low melting points and boiling points. So many covalent compounds are gases at room temperature. Conducts electricity when melted, that would be true of ionic compounds. So now looking at the structures and the way that we put together covalent electron dot structures, I've got the rules in my lecture notes. They give some rules over here. They're roughly the same order. If you follow the rules, you will always get the right answer. So the first thing you do is say, well, the first atom listed is central. So I'm going to put that front and center. Now, if it's a hydrogen, that can't be the case. So you move on to the next atom. But in any other case, the first atom listed is in the center, and all of the other atoms are bound to it. So SCl2 has a sulfur in the middle with two chlorines bound to it. So that is the arrangement of atoms, and you have to have at least a single bond or else those atoms aren't part of the molecule. Now we need to know how many total electrons we can distribute in this structure, and we look at the periodic table and see how many valence electrons are available. So sulfur's in group 6, it has 6 valence electrons available. And chlorine is in group 7, so it has 7 valence electrons available. So with 2 chlorines, that would be 14, plus 6 is 20 valence electrons available. And we have used 1, 2 for this bond, and another 2 for this bond. So we've used up 4 electrons out of our 20, we have 16 left. Now, we are going to place remaining electrons as lone pairs to complete octets, and we always do the exterior atoms first, and any remaining are going to go in the middle. So here's how we do it. That little 2 dots as a pair. I'm going to put 2 on that chlorine. I highlight the chlorine and click on it to add electrons. 2, 4, 6 there. 2, 4, 6 there. So now I have distributed a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons. I still have 4 more because there were 20 to start with. So those 4 go on the sulfur right there. And then I'm going to evaluate the structure and see, does every atom have a full shell? That is 8 electrons for almost all the atoms. And if I had hydrogen, it would just need 2. And I can verify that, yes, this chlorine sees 8 electrons because it has 3 lone pairs plus a bond. This sulfur has 2 bonds and 2 lone pairs. That adds up to 8 electrons for the sulfur. And the same thing for the chlorine on this side. Okay, so for this question, the first case, they're asking me to tell how many non-bonding electrons and how many bonding electrons are shown. So these dots, these are lone pairs. They are non-bonding electrons because they are electrons in the structure which are not involved in a bond with another atom. So I have 2, 4, 6, 8, 10 non-bonding electrons in that particular structure. And then for bonding electrons, I can just see how many electrons are represented by these lines, and each line is 2 electrons. So that is 2, 4, 6, 8, 10, 12, 14 electrons are bonding in that molecule. Now here, sometimes we show those bonding electrons as a line. It's a little bit clearer and easier to see, but sometimes we can show them as 2 dots as well, just to indicate that there are in fact 2 electrons represented there. And they want to know which structure represents a molecule with the correct electron dot formula. And what we're looking for here is to make sure that everything has a full shell. That is, every hydrogen should have 2 electrons, verified, and every other atom should have 8. So this sulfur only has 6, so this is not the correct structure. Here, each chlorine has 8, carbon has 8. It looks like it's got a double bond to that oxygen. And this oxygen has 8, so that looks like it's correct. Here, this carbon only has 4, so not correct. And here, this oxygen only has 6, so that's not correct. Now they want us to draw Lewis dot structures. And in the first case, they give us HNO2. And they give us the hint that the H is bound to the O atom. They'd have to tell us that because we know that nitrogen's central. Otherwise, we would have put it on the nitrogen. So we have HNO2. And I like to start by counting up my valence electrons. I've got 1 from the hydrogen, 5 from the nitrogen, and 6 from each oxygen. And that gives me a total of 18 electrons. Nitrogen is central, and I have 2 oxygens, and they told me that the H was bound to one of the oxygens. So this is the way that it's connected, and I've used up 6 electrons. I'm just going to keep track of that. I have 12 remaining. And now I fill in electrons on exterior atoms. This hydrogen is happy because he already has 2. I'm going to put 2 here on that oxygen and another 2. So that gives it a full shell of 8 and 6 on this oxygen. That'll give it a total of 8. So I've used up 2, 4, 6, 8, 10. By distributing lone pairs of electrons, I've got 2 left. And that means they go on the central atom, which is the nitrogen. If I evaluate the structure, I can see, nitrogen is not happy. I need more electrons. So I'm going to have to share either from the oxygen on the left or the oxygen on the right. I'm going to choose the oxygen on the left because this one is already making 2 bonds and this is only making 1. So in order to keep that fair, to remove those, double bond. So this is what the structure will look like. Put that here, oxygen, bound to a nitrogen, bound to an oxygen, bound to a hydrogen. Got a double bond right there. And this oxygen has 2 lone pairs. The nitrogen has 1, and that oxygen has 2. Next, ozone, O3. We have 3 oxygens, so if each oxygen comes in with 6 electrons, we have 18 electrons to deal with. And if I have 3 oxygens, then one of them's in the middle, and it's attached to 2 others. I've used up 4 electrons, and I've got 14 left. And distribute around exterior atoms. 1, 2, 3, 4. 4, 5, 6 on that guy. 1, 2, 3, 4, 5, 6 on that guy. I've used up 12 and I have 2 left, so they go right there. And now I can see this oxygen is not sufficiently happy. I'm going to have to share from one of the oxygens. In this case, they're identical. It doesn't matter which one I share from. So I'll pick the one on the left. There we go. It's going to look like that. So 3 oxygens, 1 double bond, and this guy has 2 lone pairs, 1 lone pair, 3 lone pairs. And finally, acetaldehyde, CH3CHO. This is a condensed structure. They're trying to tell us something about the way that the atoms are connected by grouping together the hydrogens with the carbon that they're bound to. You're going to see more of that in Chemistry 1120. So I have a CH3, that is a carbon bound to 3 hydrogens, and that CH3 is attached to a CHO. And if you play around with the structure a little bit, you'll see that the only way to make that work is to put a double bond here. If I tried to make it like CHO, that wouldn't work because hydrogen would have too many bonds. If I tried to make it CHO like this, then it would be really hard to get that carbon enough electrons. So this is really the best way to do it, and I encourage you to play around with that and see how this is the structure that makes the most sense. But it's the kind of thing that you start to see after you've played around with structures like this a few times, so it doesn't hurt to just explore that. So it's going to look like this, and you're going to have 2 sets of electrons on that oxygen. Oxygen likes to make 2 bonds and have 2 sets of electrons because he came in with 6, right? So if he's sharing 2 to get 2 more, then he'll have 2 more sets of unbonded electrons. But if you count electrons, you'll see that you have that many available. 4 from this carbon plus 3 from those hydrogens makes 7, plus another 4 from this carbon gives you 11. This hydrogen brings you to 12, and that oxygen brings you to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. The following formulas are unlikely to be correct. Propose the correct or more likely formula for each of the following. And some of these are ionic and some of these are covalent. So let's pull up our periodic table, AlO3, and have a look. Aluminum's a metal and oxygen's a non-metal. So we can follow the rules for ionic compounds here. If aluminum is +3 and oxygen is -2, then the correct formula for a compound made from both of those would be Al2O3. That would be the correct or more likely formula for a compound made with aluminum and oxygen. CaCl3. Ca is over here. It's a metal. It has a charge of +2. Chlorine is over here. It's a non-metal. It has a charge of -1. So +2 and -1. I'm going to need 2 chlorines to make that work. So it should be CaCl2. H3S. Now we've got 2 nonmetals, sulfur and hydrogen. So let's have a look. Sometimes it can be a little bit easier to just fit these together like puzzle pieces. Sulfur has 6 valence electrons, and hydrogen has 1. So I can group 1 hydrogen together with sulfur here, and I could group 1 hydrogen together with sulfur here. See, sulfur can make 2 bonds, then with hydrogen atoms, and if I do that, then the hydrogens have full shells and the sulfur has full shells, and it's happy. So sulfur is only going to make the H2S molecule and not the H3S molecule. This last one is a little bit trickier, but we can still do kind of the same thing. C2OS. If we've got carbon, he comes in with 4 electrons. And oxygen comes in with 6. And sulfur comes in with 6. So sulfur wants to make 2 connections, and oxygen wants to make 2 connections, and carbon can make 4 connections, right? So the easiest way to do that would be to have carbon using 2 of its electrons to make 2 connections with oxygen, and the other 2 of its electrons to make 2 connections with sulfur. So that would give me double bonds between sulfur and carbon, and a double bond between carbon and oxygen. So it's going to look like that. So it makes more sense to have the formula COS and not 2 carbons there. That's going to be easier. All right, which one of the following contains a triple bond? What we're going to do here is draw out the actual structures of each of these and determine which one has a triple bond. So starting with HCN, step 1, count valence electrons. I get 1 from the hydrogen, plus 4 from the carbon, plus 5 from the nitrogen, so I have 10. Carbon must be central because hydrogen cannot be. So the carbon's in the middle of the hydrogen and the nitrogen. I've used up 4 electrons. I have 6 left. I distribute those on exterior atoms. Hydrogen doesn't want any. I've used all 6 electrons. I'm out of electrons. Now I see that the carbon wants more, so I'm going to have to move a pair of electrons there. That's still not enough, so I'm going to have to move another pair of electrons there. And now I have the right structure, and it indeed has a triple bond. So that looks like it's probably our right answer, but let's just make sure. If we've got C2H4, I have 2 carbons. They each come in with 4 electrons, 4 hydrogens, each with 1 electron. That's going to add up to 12 electrons. Now we have 2 carbons. They're both central, and the hydrogens are distributed around them. So 2 hydrogens on each carbon. And I've used up 2, 4, 6, 8, 10 electrons. I've used up 10. I only have 2 left. Now the hydrogens are all happy because they only want 2 electrons. That's what they have. So I've got 2 electrons. I can either put them on the left-hand carbon or the right-hand carbon. But whichever one I put them on, the other carbon won't be happy. So I'm going to put them in the middle so that both carbons get a full shell, 8 electrons. So this structure has a double bond, but not a triple bond. For CS2, carbon comes in with 4 electrons. I have 2 sulfurs. They each have 6 electrons. It's going to be 12 plus 4 is 16 electrons. And carbon in the middle, 2 sulfurs attached. I've used 4 electrons. I've got 12 left. And I distribute around exterior atoms. So each sulfur needs 6 more to have full shell. That gives me 12. I've used all 12 electrons. I have nothing left. So now I can see the carbon's not happy, so I can share 2 of those electrons here. Still not 8, so share 2 of those electrons there. And now I can see, okay, everything has a full shell of 8 electrons, so it's going to look like this. So this structure has 2 double bonds, but not a triple bond. And finally, O2, I have got 2 oxygen atoms. They each have 6 electrons. That gives me a total of 12. So O, I've used 2 electrons. I have 10 left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The oxygen on the left doesn't have sufficient, so I'm going to move 2 of those here. And now I have distributed 10 electrons, and that's happy. So this oxygen molecule has a double bond, and the HCN is indeed the only one which contains a triple bond. This next question has us looking at molecular shapes. And in order to correctly predict the molecular shape, we first have to have the correct Lewis dot structure. So getting the Lewis dot structures down is kind of a fundamental. It's going to be really important for this class. But once we have them, then we can predict the shape a molecule will take. And this is important because although Lewis dot structures are really good at helping us see and understand how electrons are distributed, they are not so good at showing us what the shape of those molecules are. And that's going to be important for predicting things like molecular polarity, intermolecular forces, and physical properties. So the theory that we're looking at here is called valence shell electron pair repulsion theory, or VSEPR. And here it is in your lecture notes. I go through it in detail, but at the end I've got a little chart And this chart is slightly different than this chart in that I've got electron, here they call it electron groups, I call them electron sets. And they have lone pairs. And what they're calling the shape is what I'm calling the molecular geometry. And there are some small differences, like I call this trigonal pyramidal. They just call it pyramidal. And then they include the bond angle. What they don't include on this chart is the electronic geometry. And that's important to me that you see the electronic geometry because it's part of the logic of understanding why it is that, say, 3 electron sets end up with these 2 types of molecular geometry and so on and so forth. So on an exam, I might ask you about electronic geometry and I might ask you about molecular geometry, but here in Mastering Chemistry, they're only going to ask you about molecular geometry or shape, essentially. So let's look at these structures, and they give us these generic XY structures, so they're not telling us what they are. But we can compare what we see to this table to predict what the molecular geometry of these molecules is going to be. So for instance, this one here, my central atom X appears to have 4 electron sets or electron groups. That is 3 single bonds, a single bond is an electron set, and 1 lone pair. A lone pair is also an electron set. So 4 electron sets, and one of them is a lone pair here. 4 electron sets means my electronic geometry is tetrahedral. That is the geometry of the electrons. All 4 of those electron sets are arranged in this kind of spatial geometry. And then if one of those is a lone pair, then my molecular geometry, which is referring to the shape of the atoms in the molecule and no longer looking at the electrons, that's trigonal pyramidal. So this is going to go pyramidal. In this case, I have 3 electron sets. 1 single bond is 1 electron set. A double bond still only counts as 1 electron set. And the lone pair is 1 electron set. So all those are 3 electron sets and 1 is a lone pair. So 3 electron sets with 1 lone pair, that will be a bent structure. This one has 4 single bonds, so that would be 4 electron sets with no lone pairs. So that is going to be tetrahedral right here, 4 electron sets, 0 lone pairs, tetrahedral. This one has got 4 electron sets because each lone pair counts as 1 set and each single bond counts as 1 set. So 4 sets with 2 lone pairs. 4 sets gives us tetrahedral electronic geometry. 2 lone pairs means that the atoms in the molecule are making this bent shape. So this is also bent. It's a different kind of bent though, right? This is bent with a bond angle of 109 and this is bent with a bond angle of 120. We still just call both of those bent. In this case, I appear to only have 2 electron sets, 1 bond here, 1 bond there, but no lone pairs. So 2 electron sets is always linear. This one has 3 electron sets with no lone pairs. So 3 electron sets means trigonal planar electronic geometry. Note always, if there are no lone pairs, then your molecular geometry is the same as your electronic geometry. So 3 with no lone pairs is trigonal planar. This one has 2 because, again, a double bond only counts as 1 electron set. So 2 double bonds is 2 electron sets, so that's linear. And this one has 3 electron sets, no lone pairs, so that is trigonal planar. Now predict the 3-dimensional shape of these molecules. Before I can do that, I have to draw the Lewis dot structure, because the Lewis dot structure is going to tell me how the electrons are distributed and how many electron sets that I have. So let's do each of these, starting SiF4. Here I have silicon, it's in group 4. I have 4 fluorines, they each have 7 electrons. So I have here a total of 32 electrons. Silicon is in the middle because it's listed first. Fluorines all around the exterior. And then I fill in, let's see, I have 2, 4, 6, 8. I've used up 8, so I have 24 left. Now I need to fill in electrons on exterior atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all 24. I have nothing left. And silicon is already okay because it already has 8. So that is the structure of SiF4. Now we can come here and say, well, I have 4 bonds, so that's 4 electron sets, no lone pairs. So the shape of that molecule is actually tetrahedral. So even though with my Lewis dot structure, I drew it like it's a cross or a T shape or a plus sign, in fact, this molecule looks a little bit more like this. And again, we're using that dashed line to indicate that it's going into the board away from you or into the screen away from you. And this wedge indicates that it's coming out towards you. So it looks like this little tetrahedral shape. By the way, they call it tetrahedral because if you connect all of those exterior atoms, then you get this little tetrahedron shape with 4 sides. So that's tetrahedral. Next, we have CF2Cl2. And carbon comes in with 4. I've got 2 fluorines. They each come in with 7. And I have 2 chlorines. They each come in with 7. And so we get a total of 4 plus 14 plus 14 gives me 32. And if you do this enough times, you might start to see some repeating patterns. Here I've used 8 electrons. I've got 24 left. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all 24. I have nothing left, and that's fine because carbon in the middle is happy. Notice SiF4 and CF2Cl2 have the same structure, and that's because both silicon and carbon, the central atom, came from group 4, and they each have 4 atoms that all came from group 7. And so they end up with the same construction. My central atom carbon here has 4 bonds with no lone pairs, so it also is tetrahedral. For SO3, sulfur's in group 6, as is oxygen. So I have 4 atoms at group 6, so I have 24 electrons here. Sulfur's in the middle, and I'm attached to 3 oxygen atoms. That uses up 6 electrons. I have 18 remaining. If I distribute on exterior atoms to fill the octet for each of these oxygen atoms, I'm going to need to add 6 to each, and that uses up all 18 of my remaining electrons. I have nothing left, and so I'm going to have to move 2 of those into the middle in order to make an octet for the sulfur. So in the end, sulfur has 3 electron sets because the double bond counts as just 1 electron set, and no lone pairs. So 3 electron sets with no lone pairs is trigonal planar. So it actually looks like this. So again, even though I've drawn it as if it was this kind of a T shape, the shape of this molecule actually looks something more like this, where each of these oxygen atoms is pointing towards the corners of an equilateral triangle. They call this planar triangular. I call it trigonal planar. Same thing. Okay, next we have BBr3. And boron is one of the exceptions to our octet rule. I'm not going to test you on that, but may as well tell that to you. Boron's in group 3, so it brings in 3 electrons. And I've got 3 bromines. They each come in with 7, so that gives me 21. So I have a total of 24 electrons here. And boron is in the middle because it's listed first. And it has to be connected to 3 BRs, because if I don't have at least single bonds, they're not part of the molecule. And here I have used 2, 4, 6 electrons, and I have 18 remaining. So if I distribute these along exterior atoms, I have 2, 4, 6 for this bromine, 8, 10, 12, 14, 16, 18 electrons. I've used up all 18 electrons, making sure that my exterior atoms are full and the boron is not. Now here we're going to stop and say this structure is sufficient because since boron only came into the game with 3 electrons, he can't really expect the bromine to share more. Okay, so boron is an exception in that he will be okay with 6 electrons, and you can stop there. That's 3 electron sets, no lone pairs, so that is also planar triangular. But one thing I want you to note is if you said, look, this bromine might share, I could get a double bond. In that case, you would still have 3 electron sets and no lone pairs. So distributing them in that way to give boron an octet would still get you the right answer here. Finally, we have NF3. So nitrogen is in group 5, so it's got 5, and I have 3 fluorines, and they're in group 7. So that's 21 plus 5 gives me 26 electrons. Nitrogen's in the middle. If I have 3 bonds to fluorine atoms, then I've used up 6 electrons, and I have 20 remaining. So I distribute these around the exterior atoms, and that fluorine needs 6, and this fluorine needs 6, and this fluorine needs 6. So I've distributed now 18 electrons, and I have 2 remaining. That means those last 2 go on the central atom. And when I evaluate the structure, I can see the nitrogen's happy. I don't need any double bonds. We've got 8 electrons around each of my atoms. And this nitrogen has 4 sets of electrons. That is 3 single bonds and a lone pair. So with 4 sets of electrons, I am tetrahedral electronic geometry. And with one of those being a lone pair, then I am trigonal pyramidal molecular geometry. They call it pyramidal. Next, which of the following has a pyramidal shape? So here now you have to draw all of them to figure out which one is the pyramid. But you can do a few shortcuts here, and that is to say, first, listen, I can't be trigonal pyramidal unless I have 3 exterior atoms, right? I might still have to draw the structure to see if I have a lone pair or not, right? Because I can have 3 exterior atoms with no lone pair, as in this case, or 3 with a lone pair, as in this case. But if I don't have 3 exterior atoms, I can't be pyramidal. So I can eliminate H2O. It can't be H2O because that would only have 2 hydrogens attached to the O. But I do have to write out BF3, PCl3, and SO3. So if we draw out BF3, boron is in group 3, 3 fluorines in group 7. That gives me a total of 24 electrons. Boron in the middle, 2, 4, 6 electrons, just to attach those. 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. I'm all out of electrons. Boron doesn't have sufficient, but I could make a double bond, or better option is just to leave it because boron only came with 3 into the game. So boron has 3 single bonds, no lone pairs. This is planar, trigonal planar, so it does not have a pyramidal shape. It's not BF3. PCl3, I've got phosphorus is in group 5. 3 chlorines, they're in group 7. That's 21 plus 5 is 26. So phosphorus in the middle. 3 chlorines, I've used up 6 electrons. 8, 10, 12 to bring that chlorine up to full. 14, 16, 18, 20, 22, 24. And now the remaining 2 electrons go in the middle. And so here it appears that phosphorus has 4 electron sets. 3 of them are single bonds and 1 lone pair. So 4 electron sets with 1 lone pair, that would be pyramidal. So I think it's PCl3, but I'm going to check on SO3 just in case. So sulfur has 6. I have 3 oxygens. They each have 6. That adds up to 24 electrons. Sulfur in the middle, 2, 4, 6, just to put those oxygens around it. 8, 10, 12, 14, 16, 18, 20, 22, 24. So I'm all out of electrons, so I'm going to have to move at least 2 of those over there to make that sulfur happy. The sulfur has 3 electron sets, no lone pairs, so it is trigonal planar, and PCl3 is the right answer. Now this one is looking at condensed structures. Again, this is something you're going to see a lot more of in Chemistry 1120, and they have condensed the structure such that all of the hydrogen atoms are associated with the carbon atoms they're attached to. And otherwise, they're trying to show the order in which these things are attached. When you look at organic molecules, with the number and types of different atoms they have, there's actually multiple ways to draw those structures that would be perfectly valid. So using a condensed structure is one way that we can communicate more clearly exactly what's attached to what. So if I expand this out, this condensed structure, I'm basically expanding the sections which have been condensed together. So instead of just writing CH3, I'm drawing that carbon with his 3 hydrogens and then his connection with the carbon next door, and so on and so forth. And carbon always makes 4 bonds, and oxygen, because he comes in with 6 electrons, likes to make 2 bonds and have 2 lone pairs. And nitrogen, being from group 5, likes to make 3 bonds and then have 1 lone pair. So this is the expanded Lewis dot structure for this guy here. Now I'm asking you questions about geometry, and the first thing you should note is it would be nonsensical for me to ask you, what is the geometry of this whole thing? Because that's a big, complicated molecule. It doesn't have a simple geometry. But I could point at an individual atom, for instance, carbon atom A, this one right here, and say, what's the geometry surrounding this atom? And you're going to follow the same rules. This atom has 1, 2, 3 electron sets. This atom has no lone pairs. And so 3 electron sets with no lone pairs has a geometry that is planar, trigonoplanar. What is the geometry around carbon atom B? That's this one here, or this one here. And you'll see this carbon atom has 1, 2, 3, 4 single bonds, no lone pairs. That gives it tetrahedral molecular geometry. Again, 4 electron sets, no lone pairs, tetrahedral. Finally, carbon atom C right here. I have 4 electron sets, no lone pairs. So again, that is going to be tetrahedral. Okay, so nonsensical for me to ask the geometry of the whole thing, but I can point at individual carbon atoms and you can tell me what the environment looks like there. Okay, next we're looking at the same kind of thing, but instead of an expanded Lewis dot structure, I'm looking at a ball and stick model of methionine. And so your little carbons are these little black or gray balls. Your yellow atom is a sulfur. Your red atoms are oxygen atoms, and your blue atom is a nitrogen, and all your white atoms are hydrogen. So this is great. You can actually see a little bit of the 3-dimensional shape of this whole molecule, and you can see, hey, around this position, there's your little tetrahedron. This does a much better job of illustrating it than I could do. So again, it's the same thing. You actually don't have to know which atoms are which, because you can hopefully see these shapes here, right? So A, right here, this geometry, that looks like bent, right? Molecular geometry is looking at just the atoms anyways. So this looks like a bent line. Atom B here is connected to 4 things, and hopefully you can see that tetrahedron. These are in the line, and this is coming out towards you, and that's going back away from you, so that is tetrahedral. Atom C is also connected to 4 things, right? 2 carbons, hydrogen, and a nitrogen. And this is in the plane of the screen here. It looks like this nitrogen is coming out towards you, and this hydrogen is going back away from you, so that is a tetrahedral. Atom D here is only attached to 3 things. It doesn't have a lone pair because it has 8 electrons across those 3 electron sets. So that is trigonal planar. That's basically this carbon right here. And now this one is this nitrogen here. This amino acid is similar to that amino acid. This is the part of the molecule that's different. But you have a nitrogen, and what you don't see is the lone pair that's attached to it, but there is a lone pair, and that makes this not flat, but a little bit puckered. And I'm not sure if you can see that based on the shading, but this is a trigonal pyramid. And if you drew out the structure like this, you would see, oh yes, it has a lone pair. So that must be a little pyramid. This is shown as a flat plane. And I hope you can see from the perspective how this one flat plane is different from this kind of puckered guy. Okay, that is it. This is a rough assignment, guys, so make sure that you Go slowly, take your time, don't eyeball it, write it out, and make sure that you understand, because this is the foundation then for everything we're going to do on the next homework assignment too. So I hope this was helpful. Have a great day.